Swayam Prabha. Digital India. Educated India.
So, then we go with the electrostatic free energy. So, what is the principle of electrostatic free energy? This interaction between two charges, one is charge, positive charge, one is negative charge. We can do it in two different ways. Either you can identify the atoms which can be able to form an ion pair, high potential to form ion pair. In this case, you can see the positive charge atom, right, for example, which residues? Lysine, arginine and histidine, and the negative charge residues glutamic acid and aspartic acid. Right, see the nitrogen atom in the positive charge and the oxygen atom in the negative charge, and see the distance. Right, we can use the different distance cutoff, and you can see up to 4 to 6 angstrom we can use for the ion pairs. Right. So, if we take the 4 angstrom, we can get the potential ion pairs, and we can extend up to 6 angstrom, but there will be weak salt bridges even that you can account if you use the distance of 6 angstrom. So, in this 4 angstrom, right, for example, this is the one atom, this is the N, and here this is the O. You can calculate the distance, and the distance should be less than 4 angstrom, and then see the location of these atoms, whether they are buried or it is exposed. If it is buried, it contributes more than they are exposed. Buried, what is the definition for buried? The accessible surface area, you can see with less than 5%, you can see this buried. So, in this case you put 3 kilocalorie per mole, and for the surface one we can take 1 kilocalorie per mole for the standard case. To avoid the deep calculations, you can see the ion pairs based on just distance and give the weightage to each ion pair, you can see the contribution from the ion pairs, or you can directly calculate. How to calculate directly the electrostatic free energy? So, you can use E is proportional to the product of these charges and inversely proportional to the distance between them. So, you can see Q1 and Q2, they are the charges of these two atoms, and R is the distance between them. What is the epsilon? That is the permittivity of the medium. So, you can see this is a vacuum, right, you can see this value. So, in this is given as 1 by 4 pi epsilon 0, or you can use epsilon as 80 for the water and 4 for protein. So, you have the Q, we know that, R we know, epsilon we know. In this case, for any case you can calculate the electrostatic free energy. So, Q1 and Q2 we know the predetermined parameters for 20 different amino acid residues. For example, glycine, so they have different atom types, right, because based on the linkage and the location of each atom, this O N, Ct and CO, right, we give the data. So, now we have the Q1, we have the Q2. So, with the distance we get from the 3D structures, because the 3D structures we get XYZ coordinates. So, R we know, then Q also we know that. In this case you can easily calculate the electrostatic free energy. So, we can calculate the hydrophobic free energy and the electrostatic free energy. So, how to do the hydrogen bonding free energy? So, what is hydrogen bonds?
Hydrogen shared by 2 atoms.
Hydrogen shared by 2 electronegative atoms, right. This is interaction, right, for the hydrogen bond atom with the electronegative atom plus another electronegative atom. For example, if you see the atom attached to the hydrogen, this is called donor, right, and the one which accepts this hydrogen, right, this is the acceptor. So, we need 2 electronegative atoms like this A and D, right, one is attached with hydrogen. So, and the distance between this acceptor and donor, this is about 2.3 to 3.3 angstrom, right, approximately you can put 3 angstrom between the 2 heavy atoms, right. This is how we identify the hydrogen bonds, right, in systems. So, now we can identify these hydrogen bonds, right, in the protein structures. How to identify the hydrogen bonds? Because we have the coordinates, so we know the distance. So, we put the donor and acceptor, right, this they are within the distance of 3 angstrom, right. We can use this program HP plus to get the hydrogen bonds in protein structures. It will give you the main chain hydrogen bond, main chain side chain hydrogen bond and side chain hydrogen bonds and all. So, approximately we can put 1 kilocalorie per mole actually hydrogen bonds you can have 1 to 5 kilocalorie per mole. So, to approximate we put 20 kilocalorie per mole for the different situations, and then you can calculate the total energy in a protein due to hydrogen bonds. For the hydrophobic free energy, how to calculate the total free energy due to hydrophobic free energy?
Using
We use accessibility, atomic solution parameters, use for all atoms and sum up, and we get the data. For the electrostatic free energy, get the ion pairs and give weightage to each ion pair we can get, otherwise you can use the distance and the charge, directly calculate the electrostatic free energy. Hydrogen bonds, you can see the hydrogen bonds, right, approximately you can see about 0.73 hydrogen bonds per protein. So, in this case we see the hydrogen bonds, right, and then see different weightage to the each hydrogen bond and see the free energy due to hydrogen bonds. So, now see the van der Waals interactions. So, how to explain van der Waals interactions? For example, if the two atoms are very far, right, then what will happen?
They attract.
So, if it is very far, then very distant, then no interaction, no interactions, right, that is very far. When you come close to each other to some distance r, then what will have, it will have the, they have the attractive force at a minimum distance of r, they will come close to each other to at minimum at a distance of r, you will have the attractive force. When it is very close, right, very close to each other, then what will happen? It will have the repulsive force, finally it is dominated by the repulsive interactions. So, we can use this graph to explain the attractive force and repulsive force as well as net force. So, here this red one, this attractive force, which is very far away, there is no attractive force. At some point of distance, like the x axis distance and y axis the electrostatic potential, you can see say force or the energy, right. So, if you see to some distance, that we have the attractive force, that is favorable interactions. Then we go closer to each other, again more closer, if you see more closer, then it is because of van der Waals this repulsion, the high repulsive interactions, right, you can see this is the green one, it dominated with the repulsive interactions. So, combine these two together, you can have the Leonard-Jones potentials, right, this is the graph, how they look like. So, we can derive this equation, right, using these graphs, right, using a 6L potential. This energy is equal to Aij by Rij power 12 and Bij by Rij power 6. Here this is why this is called 612 potential, because the power of Rij power 6 and Rij power 12. If this is separation is very small, which term will dominate? Repulsive will dominate. So, you can say R12 that is very high, because it is very close, then repulsive will dominate, you will have high repulsive energy. Then if you move together, then the Rij 6 will dominate, then you have the attractive force, then you have attractive interactions. So, here which is attractive term, which is the repulsive term?
Positive
is repulsive term and the negative is attractive term. So, from this you can estimate the interactions due to van der Waals free energy. So, here you can see this, here we have two constants Aij and Bij. This Aij and Bij depends upon the van der Waals radius and well depth, right. What is van der Waals radius and van der Waals well depth? Right, we as we discussed, it is a combination of attractive and repulsive forces. So, we will get a graph like this, and you can see that this is the depth, right. So, from here for the equilibrium distance, okay. So, you can see you get the well depth. So, on the particular distance r, okay, this is the distance r, where we have the highest attractive interactions. So, this is called this r, that is called the van der Waals radius. So, from this graph you can calculate the van der Waals radius as well as van der Waals depth, this is the epsilon and r. So, using this radius and well depth you can calculate Aij and Bij. Then this equation we know Aij, we can calculate Bij, and Rij we can calculate from 3D structures, right, because we have the coordinates, we can calculate the distance. If you know the distance, we can easily get the Ri power 6 and Ri power 12. So, for each atom, so we have these specific values for the radius and well depth, right, the predetermined parameters, right. You can see this is the Rij and epsilon for different types of atoms, whether it is carbon or the C alpha carbon or the different types of atom types, you can have this well depth as well as the radius, you can use that. So, we discussed about 4 types of interactions. Then also we have disulfide bonds. The disulfide bonds, how disulfide bonds are formed? In the oxidative environment, if you between the two cysteines, right, you can see the S. So, finally, it get the disulfide bonds. So, disulfide bonds are stronger bonds, and if you see the side mutation experiments, For example, if you mutate a cysteine to another residue and the cysteine makes disulfide bonds, then how far the energy is lost, change in free energy. Or if you replace any amino acid to cysteine and cysteine makes a disulfide bond, how much energy you can gain, right. If you see, this is about 2 to 5 kcal per mole, right, depending upon the location and the environment. Approximately we can take this as 2.3 kcal per mole for each disulfide bond. So, can we see disulfide bonds in all proteins? No, right. Approximately about 20 to 30 proteins only we have the disulfide bonds, because we have cysteines and they form disulfide bonds. So, then we have the tendency of forming disulfide bonds. If we have the 3D structures, can we identify the disulfide bonds?
Yes.
You can see, right, you can see the disulfide bonds based on the distance, right, and each protein we know how many disulfide bonds. Based on that you can calculate the free energy due to disulfide bonds. Now we calculated almost all the free energies at the folded state enthalpy terms. Now we go with the entropy term. So, right, this is a randomness, we can calculate minus C in delta S. Delta S you can calculate the probability of a residue in a specific rotamer. So, in this case you can see delta S equal to minus R into delta Pi in ln Pi. This is the probability of a residue, right, in a specific rotamer in a specific conformation, right, rotate around any single bond. How many conformations each atoms can take. Or you can use this equation delta S R into logarithmic of z power x, where x is the number of flexible points where we can rotate and z is the number of orientations at equal energy, where the two places where you can have the orientations. Using these equations you can calculate T in delta S. This is due to entropy. Then I discuss the unfolded state is not completely unfolded, there are some interactions. To account that we take 50% of the hydrogen bonds, we assume they are in the unfolded state, and this is the assumption. So, if you can do that, then non-entropic term also we can account to some level. So, now we have the entropic term, we have the enthalpic term, and this is the example for different proteins, but if you calculate now you can see the little bit differences because of the resolutions and other changes. Also we use various approximations in this model. Now we can calculate set of proteins and take the total, what is the total value of hydrophobic free energy, electrostatic, van der Waals and all the free energies, and take the sum of all all the energies, all energy. Then we normalize to 1. So, this add up and divide with this total energy. So, then normalize to 1, right. If you do this, then you can see approximately the hydrophobic interactions contribute to 50% and the hydrogen bonding up to 27%, van der Waals 15%, electrostatic 6% and the disulfide 1%. Then we look at these numbers, whether these numbers make sense. So, because the hydrophobic interactions are dominant, because most of the proteins they follow the hydrophobic collapse model, and to make these hydrophobic residues to be at the interior of the core when the protein folds from the unfolded state to the folded state. That means hydrophobic force is the driving force, right, for many proteins, and this is the reason why this value of more than 50% in the case of the hydrophobic free energy. Then we look into the second term, hydrogen bonding free energy, right. What are the major secondary structures form this hydrogen bonding free energy? Alpha helices and beta strands, right. Secondary structures are mainly formed by hydrogen bonds, right. If you see a protein structures, predominantly you can see the occurrence of alpha helices or beta strands. In this case, the hydrogen bonding free energy also plays an important role. So, if you see this number, this is 27%, right, that is also reasonable. Then if you see the electrostatic interactions, so you can see a limited number of ion pairs between the positive charge and the negative charge, right. In this case you can see about 66%. Disulfide bridges are strong, but why the percentage is less? Because it is rare, because many proteins they do not have the cysteines or disulfide bonds, and even if the proteins have disulfide bonds the number is less. This is the reason why the number is less in this case. So, from these numbers we can tell that the hydrophobic interactions are dominant and it is a driving force. It makes the unfolded state protein to initiate folding. When it starts folding, then the other interactions like hydrogen bonds give the shape, for example the secondary structures alpha helices and beta strands, and the van der Waals electrostatic interactions, and keep the protein in a stable state, right. So, hydrophobic interactions initiate folding and the other interactions they give shape and keep the protein in a stable state. Now, the question is, if we have these interactions, is it possible to predict the free energy change for any protein of known structure? Yes, because if you see the delta G values, they are known only for 300 to 500 proteins, but we have the structures. How many structures are known at the moment? 130,000, right. In this case we have more structures, but the stability values are known for less number of proteins. So, is it possible to predict the stability from structural information? So, we can relate, right. For example, if you have a set of proteins, for example 100 proteins, if you know all the 100 proteins, you calculate all the contributions as we discussed now, right. If you have the structures, we can calculate the interactions, right. So, in this case you can calculate all the values, right, all these free energy values, and experimental value also we know. So, then we use the principle of least squares to obtain the coefficients, right, because we can write y equal to mx plus c if there is only one variable. If it is more, we can extend. In this case we have different contributions, okay, this is the constant and we have the different coefficients. So, use the principle of least squares, you can get the coefficients, right, and for any protein you can calculate the free energy contributions, and then using this equation, right, you can predict the stability of any proteins of known structure. So, in this case you have the value for the experimental data, and if you know the structures you can use these contributions to predict the stability. For a set of proteins we can see is a good correlation between the experimental and predicted values, the deviation is very less, right. This was done with less number of proteins, but now we have more number of proteins available, right. You can extend it and you can refine the values. In this case it can be applicable to all the proteins of known structures, and you can do the analysis for the different proteins with different stabilities. Fine. Summarizing, what did we discuss today?
Protein stability.
Protein stability. What is the protein stability?
So how
Is the free energy difference between folded and unfolded states. What are the major contributions in the folded state? Hydrophobic energy, electrostatic energy, van der Waals energy, right? Disulfide bonds, hydrogen bonding energy, and so on. So, in the case of unfolded state, what is the major force in the unfolded state? Entropy, right. So, now if you know the 3D structures, you can calculate all the energy terms and you can relate these values, right, to understand the contribution of different energies as well as to predict the free energy using 3D structures. In the following classes, we will discuss about the stability of proteins based on amino acid substitutions. For example, what will happen if you mutate a specific residue in the stability, and if you have structures, which residues which contribute to the stability, which residues are important for the stability, and so on, right. And then we will discuss about the folding rates or interactions and so on. Thanks for your attention.